When a liquid metal cools and solidifies, its internal atoms arrange themselves into specific crystalline structures. The primary challenge in materials engineering is predicting exactly how those microscopic arrangements will dictate the strength, flexibility, and behavior of the metal at the macroscopic scale. Engineers do not guess at these properties. They rely on equilibrium phase diagrams, precise thermodynamic maps that plot the relationship between a material's atomic structure, its chemical composition, and its temperature. This chart shows the metastable iron-iron carbide system. It is the foundational diagram for all steel metallurgy, detailing every physical state iron can take as carbon is added to it. The lines drawn across this map represent the precise path of lowest free energy. They indicate where an alloy will naturally transition from one state to another, seeking the most stable configuration possible as it cools.
Historically, these phase diagrams are viewed as purely empirical. They are treated as observational maps, compiled from decades of physical experimentation, rather than expressions of fundamental geometric laws. Looking closely at this phase diagram, three vital coordinates define the transformation of steel: the peritectic, the eutectoid, and the eutectic points. These three intersections dictate the absolute limits of structural phases, defining the maximum solubility of carbon in iron. They occur at highly specific mass percentages: 0.18%, 0.76%, and 4.3% carbon. Recent mathematical analysis suggests these exact carbon percentages are linked to one another by the golden ratio, the geometric constant of 1.618, denoted by the Greek letter phi. This observation aligns with Adrian Bayesian's constructor law, a principle stating that all flow systems in nature evolve configurationally to provide easier access to the currents that flow through them, determining universal shapes and structures. The question is whether the presence of the golden ratio at these structural boundaries is a mathematical coincidence or an indicator that the thermodynamics of steel follow the same geometric optimization found in the constructor law. To test this, we examine the bottom left quadrant of this chart, covering the Hypo Eutectoid steel region from 0 to 0.76% carbon. This is the most critical region for construction and engineering. At room temperature, the physical microstructure of steel in this specific region consists of two distinct phases: pure iron, called ferrite, and a lamellar composite of ferrite and cementite, pearlite. The baseline equation for this two-phase structure is straightforward. The weight fraction of pearlite equals 1 minus the weight fraction of ferrite. In our hypothetical model, we force the ratio of these two physical structures to match the golden ratio. If a purely mathematical constant can accurately predict the physical mass percentages of an alloy, it suggests that equilibrium structures are geometrically deterministic, not just empirically observed. Formalizing the hypothesis gives us our starting calculation: the weight fraction of ferrite divided by 1 minus the weight fraction of ferrite equals 1.618. Solving this algebraic equation isolates the required weight fraction for the ferrite phase. The result is 0.618. To ground this fraction in physical reality, we use the known equilibrium boundary conditions at room temperature. Pure ferrite holds 0.008% carbon, while pearlite holds 0.76% carbon. We build a mass balance formula for the total carbon percentage of this phi-derived alloy. Plugging in 0.618 for the ferrite fraction yields 0.295% total carbon. The inverse calculation, setting the pearlite to ferrite ratio to 1.618, produces 0.467% carbon. We have just generated two distinct carbon mass percentages, 0.295% and 0.467%, derived entirely from the geometry of the golden ratio. Mapping our theoretical 0.295% and 0.467% markers onto the x-axis of the phase diagram subdivides the hypoeutectoid steel region. Adding these golden ratio-derived percentages gives a sum of 0.762%. This perfectly matches 0.3, the defining eutectoid point mapped at 0.76%. The defining microstructural boundary of steel correlates with the geometry of the golden ratio. Standard steel possesses a maximum carbon solubility limit of 2%. The immediate question is whether this geometric relationship breaks down once we pass that threshold. Expanding our view to the cast iron region, two extreme limits define the system: the eutectic point at 4.3% carbon, and the absolute cementite limit at 6.67%. Dividing these extreme values by the 2% limit of steel maps directly to continued fractions of phi. The macro architecture of the entire iron-carbon equilibrium system is scaled by this single geometric constant. If this alignment is truly driven by constructor law, it should appear in materials other than iron. This is the copper-zinc phase diagram, the foundation for brass. In the alpha region, maximum solubility of zinc and copper occurs at 38%. Calculating the mass proportions here, 62% copper divided by 38% zinc yields 1.63, matching the golden ratio. We see a similar trend in the copper-tin phase diagram, used for bronze and specialized solders. The epsilon intermetallic compound formation zone peaks at 37.2% tin. The mass ratio here, 62.8% copper divided by 37.2% tin, is 1.69, again nearing the golden ratio.
These calculations suggest that three significant engineering alloy systems, steel, brass, and bronze, consistently converge toward this specific geometric proportion at their absolute limits of thermodynamic stability. Solidifying metallic alloys will relentlessly seek the path of least resistance to shed free energy and achieve absolute equilibrium. Under the constructal law, this path of least resistance is a geometric phenomenon that determines how structures evolve for maximum access. The presence of the golden ratio at the critical limits of phase diagrams is a signature of quasi-symmetric proportionality dictating the foundation of materials engineering. When engineers consult these diagrams for stability, they are observing a recurring geometric pattern, a physical manifestation of nature's drive toward thermodynamic equilibrium.